So, welcome to this talk, and if you don't hear me well, just let me know, because the April weather was playing with my voice, snow and sun. So what I want to talk about is interactive symbolic testing. It's like a relatively new thing in what we have been doing at Apalache over the years. And of course, some people maybe came for this word, it's LLMs. I'm going to tell you about how we are using these things together. And now I have to click. So if you don't know Apalache, which probably is not the case, I just want to remind you that there is another model checker called Apalache, not just TLC. It's a symbolic model checker that translates TLA plus, at least a fragment of TLA plus, to SMT, and checks invariants using the SMT solver called Z3. And I just realized that we actually passed the 10 years mark. It's kind of a small birthday for Apalache. It's 10 years old now. And over the years, it was supported by different foundations. Like in Vienna, it was supported by INRI, Interchain Foundation, Formal Systems. And now, finally, it should join the TLA Foundation this year, if the paperwork works, right? Okay, so, and now we are talking about your own customized search and test harnesses. That's kind of the latest developments. So what I want to talk about in this relatively short talk, I will present you this new API for symbolic search in Apalache, which allows you to write your custom scripts. And then I will talk quickly about two experiments with LLMs, using Copilot and Sonnet 4.5 initially, and then using Claude Code and Codex in the later stage, which is kind of exciting. I just want to tell you what I learned on these experiments. So let's talk more or less quickly about the symbolic search of Apalache. I cannot explain you all the details. We have been developing these things for some time, but I want to give you some intuition about how it actually works. And for that, I'm not going to talk about complicated things. I'll just give you a simple example. Imagine you have a cached key-value store where you just have a single database, no replicas, just a single database, and a cache on top of it. And basically, you want this behavior if there is an entry cached in your cache and somebody accesses this entry, this key, you want to get it from the cache. And if it's not accessed or outdated, you actually want to send a request to the database, and then later the cache will receive the reply from the database, and the client will get the value from the cache. It's like a very simple cache. I made it up, kind of. I looked on the internet how it should work, made it up, but importantly, there is a time to leave, so the entries get evicted if they become too old. That's like a very simple example. You can write it in TLA. You don't have to look at this. I just want to convince you can write this algorithm in TLA+, this specification. You can go and check this link if you don't trust me. But basically, you describe this behavior of how messages are sent around, how requests are made, and so on and so forth. There are like 5 or 6 actions you can write down in TLA+. And this is fairly straightforward. If you have been writing TLA plus specifications, it's not hard. This is easy. Now, the hard part is what happens if you want to check an invariant, and there are already quite a bit of talk about this, how you use TLC, how you use other tools, and so on and so forth. So, for instance, I want to check this naive invariant, which is saying if for all entries in the cache, if the timestamp of the entry is greater than the timestamp of the last update in the store, then the entry in the cache should match the entry in the store, which is obviously false, as you probably know, but I want to check this invariant, why not, right? And on purpose, I bump the parameters here to relatively large values, which TLC wouldn't be able to handle. It will just run out of disk space, state space, whatever space. And random simulation wouldn't be able to handle it, right? So why I want to do it? Because it's kind of closer to what engineers have, because they have larger parameters, not just tiny ones. if you want to check this invariant, the very first algorithm that was implemented in TLA, in Apalache, that's bounded mode checking. That's the default mode, unfortunately, because it's the slowest one. That's why I'm saying unfortunately. But what it does, it basically, it offloads 2 tasks to the SMT solver. The first task is to find a sequence of actions that should be executed and violate an invariant. And the second task is to pick up the data values. And basically, the solver has to solve 2 tasks at once. It has to pick up the sequence and pick the data values that match this sequence, which happens to be a bit too hard for solvers, actually. So that's bounded mode checking. The good thing, it actually works, at least in this example, it works much faster than TLC. It takes about 2 seconds to find this invariant violation. You can see the violation, it's not that important. There are like 5 steps. What's important is that just before the store sends the feedback to the cache, the store is getting updated, as you probably expected from the faulty kind of, the counterexample. So you can find this counterexample. What about another invariant? Now I sat down and thought, what is a more realistic invariant for this system? So I wrote this invariant. You don't have to again understand it, but basically it's saying like if I have a value in the cache, there must have been a value in the store in the past that has exactly the same key and the same value. And for all other entries in the writes history, I also have a writes history. There must be some window where either they had a chance to update the cache or they're kind of outdated already. That's kind of the intuition. What's happening here, if I run the bounded mode checker here, it kind of works, except after 10 steps, it takes like 15 minutes to check it. And after 12 steps, it takes, you don't see it, 27 hours. You just don't see it here. But basically, it exponentially explodes in all directions, you know? And kind of 10 steps is not bad if you compare it to TLC, because TLC maybe will not make it even to 3 under this configuration. But it's still kind of slow. And that's what was plaguing us for years until we found a bit more practical approach to this problem. A bit more practical approach is to say, don't ask the SMT solver to find a schedule and the data. Just pick some schedule at random and find the data. And this is much faster. You pay with completeness for that because you randomly pick schedules, but you can pick many random schedules and then ask the solver to find the payloads many times. And that's like a more practical approach to this problem. If you look at the same example, you basically, like in the order of like 10 minutes, you can exercise 1,000 different randomized symbolic executions like this. And in practice, this approach actually finds bugs much faster than the bounded mode checker. That's why in practice, whenever I analyze TLA specifications with Apalache, I almost never use the bounded mode checker because it's just too slow. Instead, I run this randomized symbolic simulation. The cool thing is that you can get a big machine with 32 CPUs, for instance, and run these randomized symbolic simulations in parallel. Or if you have more CPUs, you can do more things in parallel. There is something interesting going on here because if you fix a schedule, if you fix a sequence of actions, somehow it's much easier for this tree to solve these problems because it does a lot of propagations and doesn't try to solve 2 problems like doing rollbacks on the control flow and doing rollbacks or backtracking, doing backtracking on data intuitively. So it's kind of, you fix one schedule, finding data is easier. It's trivially parallelizable, that's a good thing, but there is one problem with this approach, and that's what people were telling me for some years. Everybody wants to customize it. Everybody wants to say, this action has a larger probability of being fired, for instance. We want to customize it, we want to make it tuned towards our purposes. And the problem is that this thing is written in Scala. It's very hard to find someone who wants to customize this model checker in Scala. With LLMs, it's probably easier now, but in general, it's not easy. And this is the thing I want to talk about today, basically. That's like the last epoch in development of Apalache. That's a programmatic API of the same symbolic search. So instead of picking actions at random and sending them to a solver, what you can do, you have several API calls in the JSON RPC server, like load specification, assume that this transition has taken place, take the next step, assume that something holds true in this particular symbolic state, query for the current state, query for the current model, check invariance, roll back to the previous state in the symbolic execution. So you have this programmatic API, and you can do what you like with like, you can bias actions, you can prioritize schedules, you can get feedback from Apalache, you can do things in parallel, do whatever you want with this API, basically. It actually wasn't designed to work with LLMs. It was designed for other purposes, but it happened to be a good fit for LLMs because they can pick up this API and write Python scripts to work with it. And I don't want to like take too much of your time, but I just want to give you two short stories about how I used it. The first story, I wanted to apply LLMs because I didn't have a lot of experience back then with them. I wanted to apply Copilot with Claude Sonnet to symbolic testing of trivial FTP, file transfer protocol. Basically, the idea was that engineers don't want to write test harnesses, but LLMs don't mind. They do whatever you tell them, right? And the experiment was like that. Take several implementations of TFTP, write the TLA specification by hand. I wrote this specification by hand and refined it later. And AI tool should write the test harness and refine it if there are any issues. And then the test harness also runs the system under test, which is TFTP, and it runs Apalache to do this symbolic execution in parallel with implementation. Writing the specification was easy. I spent like 2 days reading the RFCs on trivial transfer protocol. There are like 4 or 5 RFCs. It was super fast. I wrote this specification was completely wrong, by the way. I thought it was okay, but it was like totally off rails. Like, I didn't understand the RFCs, I can say. And now I wrote this specification. Now comes the very first question that every engineer is asking. How does it match the implementation? That's where LLMs come into play, right? Basically, what I want to do with LLM, I want to run this loop. I have this test harness in Python generated by an AI tool, right? On one side, in the middle. On the left, I have Apalache, which loads the TLA specification, and it does all this load spec, assume transition, blah, blah, blah. The harness queries the SMT model, the state of the TLA spec for data, sends a command to the system under test, to TFTP, gets response. It's a bit harder than that, but kind of gets response, let's say. Loads the data from the response back to the SMT context, to the state of your search, and continues. And if it cannot continue at some point, you know that you have found a violation. There is a mismatch between the implementation and the specification. And you have to figure out whether it's the implementation bug or the specification bug. So that was the idea. I spent, like back in October, I spent like 5 hours writing a very detailed prompt to Copilot and Sonnet. It was super over-engineered because I thought this tool will just do magic as people promised to us, and it didn't. But it actually generated it generated a brilliant harness. It would start a lot of Docker containers. They would communicate with TFTP over small Python scripts. There is like a control script somewhere, I don't remember where. So it was like a very interesting thing. And it looked amazing, except it didn't work. So I started to use it. I looked into the harness code. There were a lot of to-dos saying like, this we'll do later, who cares? So I basically spent another week trying to debug this harness. At some point, I had to actually manually write some of the code because it was divergent, basically. It could not converge to something that worked. And I like burned all of my budgets on Copilot that I had. But it started to work after a week of this suffering. And then by the end of that week, I was a bit like, maybe I shouldn't do it again. What's interesting here, the moment it started to work, it has found about 15 deviations in the spec, the deviations from the implementation. So my understanding of the RFCs was completely broken. So I would just run these experiments, get a counterexample in a nice state chart, look at this state chart. It was all broken. So I would read an RFC again and say, okay, I didn't understand this part. So I was fixing it. I have fixed like at least 15 times, at least, actually more. But as a reward, I actually have found a bug in the end, a bug in the implementation. So in one of these implementation, actually, what happened is that at some point, under some circumstances, which is like a lot of stuff here, under some circumstances, you send an acknowledgement packet to the server, and it sends an acknowledgement packet back, which should not happen in TFTP at all. It was a corrupted packet, by the way. It was composed of 2 different responses, so there was definitely some memory issue. I reported to the author of this tool, and he was like, yeah, it says TFTP is insecure, so who cares? But it's a bug, okay? It's kind of a reward for the effort. So in the end, I actually found a bug in another implementation, which was relatively similar. And with that experiment in October, basically, what can I say? It kind of works. You can generate test harnesses. It's not effortless. It's not like what some people write on Twitter, or you just tell it, do the work, and it will do the work. It's not true, at least not in my experience. So you have to actually watch this thing. You have to define your formats. If you don't define your formats, it will go wild. It will just invent something, and you don't want to see what it invents. Even back then, it was even parsing things with regular expressions. I have never seen regular expressions in loops and all that. It's just incomprehensible. But it kind of works. Also, it does visualizations. If you want to visualize your logs or state of your execution, it's amazing. So that's the first experiment. And by the end of this experiment, I was like, are all of our specifications actually broken? Because I have found so many violations in my spec. And the reason is that, like, usually if you write a specification as a verification engineer, you abstract a lot. And it's very hard, much harder to make this specification, to make it closer to the actual implementation, because the implementation comes back and says, oh, I just sent this message again. And you're like, I don't care, it's safety. But you have to do it if you want to match the implementation. So conformance testing is a bit harder if you want to refine your spec. That's the first experiment. The second experiment, we all have heard about the quality jump in LLMs this year, kind of. And again, if you look on LinkedIn or Twitter, somebody will tell you, oh, you just write it like this. He's Zookeeper, for instance. I picked Zookeeper as an example. Write a test harness, extract the specification, do it agentically. And again, I wanted to see how it works. So that's what I did. This time, I said, I don't want to write the spec. I just chill. You know, you write the spec, you write the harness. I enjoy my life. And it should work, no? I didn't. Okay. So we are kind of almost done. Almost done. I have not found any conformance issues today. In the morning, they were still happening. That's kind of, I called it ZooMonkey. That's a Zookeeper testing framework, which tries to get out of the jail, right? And it's actually, these agents have much more autonomy now. I could keep them working like for 1-2 hours, refining the specification, but they still need a lot of human guidance. It's just as an anecdote, I told to several people at some point, one of these tools was saying, oh, I looked at a set of sent messages, and there is a small issue with this set of sent messages. I just can remove a couple of messages from there to make it work. I was like, don't remove sent messages. They're called sent messages for a reason. Yeah, so you can use this tool. That's my conclusion, but you should be careful. You need guidance here. And you see, I haven't found bugs so far. It took about 1 month of running this stuff, like 300 commits or something. I just wanted to highlight like that this thing is much larger now. So I have like 5 specifications. Imagine TLA, they're written in Python, but imagine TLA, it's not important. I have this harness, which is much better organized now. I actually wrote the architecture this time. It has an action scheduler, it has an oracle, it has a communications module that does all TCP communication, a process runner that kills processes and starts them, has an input-output queue to communicate with a replica. And I run just one zookeeper replica, not a real distributed system. I kind of wrap the whole thing with a specification, and there is just one replica here. And of course, if you try to test a system like this, there are a lot of actions, like 50 different actions. If you just do it uniformly at random, it will not progress to anything interesting. And again, I was like, Claude or Codex, I forgot which one, let's just bias actions. Let's add reinforcement learning. Let's just get feedback by using this view. A view is just an operator on TLA+. Let's just get this coverage and do some kind of simple reinforcement learning. It implemented it, it started to bias actions, assign different weights to different actions. And this kind of works. I needed a few more tricks, but it kind of works. So that's it about LLMs, and like just as another example of what you can do with this API, I just want to mention it. Don't have time for that. Another example, you can actually write a symbolic fuzzer now. You can, if you know AFL or any kind of other fuzzers, they get coverage, they kind of measure progress, they try to get deeper in the coverage, basically. And you can do the same for TLA+, but symbolically. You actually use this API to get deeper and deeper. You look in the system views, save them, and you can replay actions. It's all customizable. Yes?
Who wrote this wonderful?
Me? I mean, me and Copilot. I wouldn't claim all of it. The UX is Copilot. I could not.
So this is like AFL.
It copies exactly the behavior of AFL. Yes.
Yeah, but doing it symbolically, or?
Yeah, I mean basically AFL mutates the inputs, and I mutate the action schedules. It's genetic algorithms, but over the action schedules instead of inputs. And the rest is symbolic. You just replay the whole thing and check for invariance.
So I mean, so this is a and this is a form of symbolic AFL in some sense, but within the space of TLA.
It's for TLA+, yes. I'm still trying to understand what it is, but it's kind of cool.
Even when AFL was published, even the author would acknowledge that he doesn't understand what it's.
Yeah. It kind of finds bugs, but it's not clear when and how. Right. What I want to tell you, basically, now you don't need to use Scala, Java, whatever. Write your own symbolic search scripts. You can write them in Python, TypeScript, whatever. It's basically JSON RPC is the simplest API you can have. You just run the Apalache server and use any language you like to experiment with your symbolic search. Connect it with your code, as I just showed you. It's possible. And LLMs can now help you doing that, because in the past, engineers were kind of reluctant to do that. And LLMs, they don't complain. So actually, this API provides a nice feedback for AI tools. They can also just pick up this API and experiment with your spec, even without you doing much, which is quite interesting. They can just do curl, experiment with your spec. And yeah, obviously, when you do something, you know better what kind of search you need. And that's important. That's why you have to customize it. And another point, again, I stress it, I cannot stress it more, it's easy to parallelize if you do this kind of customized search and randomized search. That's the key takeaways. Yeah, if you want me to do some work, I'm an independent researcher now. If you want to contact me, here are my contact addresses, but also if you want to read about this tasting exercise of TFTP, it's all here. You go to Protocols Made Fun, that's my blog, and you can read about this experiment. A lot of text, I warn you, really a lot of text, but you will find the details. Yeah, thank you.